Railway innovation extends beyond efficiency. It encompasses the development of systems that are inclusive and environmentally responsible. Within the FP3-IAM4Rail project, this vision is advanced through Work Package 16 and Work Package 17. Work Package 16 concentrates on sustainable and cost-efficient eco-design for rail assets, including green tracks, turnouts, and bridge structures, while Work Package 17 focuses on additive manufacturing-based repair processes and spare parts. Together, these work packages pursue the research, development, and delivery of solutions that will be validated through system-level approaches, targeting up to TRL6. Their outcomes will be integrated into DO6, Demonstrator 6, one of the 7 integrated demonstrators that constitute the IAM4Rail project and play a pivotal role in promoting research and innovation in the railway sector. DO6 aims to showcase the eco-friendly design, production and repair of resilient assets, supported by advanced fabrication techniques such as additive manufacturing. The DO6 partners involved include Voestalpine, SNCF, ADIF, Trafikverket, DB, OBB, Technica, Talgo, Strukton and SEAT. DO6 includes 13 use cases, whose use cases are located in different sites across Europe, from Sweden in the north to Spain in the south. The use case 16.4 demo includes investigation of railway bridge dynamic factors for short-span bridges that have shown to be experiencing high dynamic amplification under train passages. The result shows that the dynamic amplification factors of the Eurocode are over-conservative. The use case will contribute to cost reductions in design and assessment of short-span railway bridges. The use case 16.4 also includes monitoring platform for the Tahoe Segura Trasvase Bridge, with the aim of early identification of abnormal behaviors in the structure and detection of rolling stock that is potentially aggressive to the structure. In the use case 16.1, Voestalpine is demonstrating a new greener turnout and optimized components such as innovative sleeper system and squat-resistant rail. The developments are expected to lower the CO2 emission, reduce time needed from design to manufacturing, and optimize maintenance procedures. Within use case 16.5, Platypus is being developed, a tool that, by using predictive AI and machine learning, can better predict flood-related risks for water-based structures. The collected inspection data is used to improve maintenance and better predict rail traffic safety during floods. The Platypus project thus improves the safety of the rail network under the constant challenges of climate change, while reducing maintenance costs by ensuring the resilience and performance of the rail network. Use case 17.1 has developed a machine for in situ rail and turnout repair using a powder-fed directed energy deposition additive manufacturing. The system integrates automated subsystems for material removal, DED powder deposition, final machining and dimensional measurement. Use case 17.2 evaluated 3 additive manufacturing technologies: cold spray, powder-fed laser-based directed energy deposition and wire-fed laser-based directed energy deposition in order to repair train wheels, a high-cost consumable, without requiring axle disassembly. The video shows the repair process using laser DED powder technology. This door panel, no longer reproducible due to the discontinued mold, was remanufactured in use case 17.5 using additive manufacturing, specifically fused filament fabrication 3D printing. Europe's Rail Digital Warehouse, from use case 17.6, enables operators to share additive manufacturing use cases, with the landing page presenting the most recent contributions for quick insight. The Europe's Rail FP3-IAM4Rail project demonstrates eco-friendly design, production and repair of resilient assets, including additive manufacturing.